Hi, this is just one short additional video that I wanted to make. It shouldn't take very long at all, but I realized that in the explanation video around electromagnetism, I didn't talk about the field near a current carrying wire and the right-hand grasp rule and the magnitude of that field. And so I feel like I need to do that now to make sure, because I actually use that formula in the example video. So a little bit of an oversight on my part, for which I apologize, but hopefully I'm doing this before you actually get to that point. So we know that if we have a charge, either free electrons, free protons, any charged substance moving in a magnetic field, they'll experience a force. But the inverse of that is that moving charges create a magnetic field as well. So if we have, let's call it a current carrying wire, is probably the simplest way to think about it, which is going in this direction and which is carrying a current in that direction of I amperes, then the field around it will be cylindrical. So if I draw the field lines, they'll be continually getting larger cylindrical field lines. Now, I don't know how good my drawing has been, but if you imagine a cylinder of field line, right, so that should be a cylinder. So maybe I should make those a bit more elliptical than I did. It's a cylinder of field lines around the wire, and the direction of those field lines is going to be given by what we call the right-hand grasp rule. So if we hold our thumb out as though we're hitchhiking, so thumb sticking out in one direction, fingers curled around into a near fist but kind of open. If the thumb is in the direction of the current, the fingers show the direction of the field lines. So in this case, at the back, the field lines are coming up, because if you grasp it, your hand will be away from you with the palm facing up and the fingers curling around toward you. So at the back, the field lines are going up, and at the front, the field lines are coming down. So they're going around in that direction, if that makes sense. So let me try to make it even more explicit by making the line at the back dotted and the line at the front solid. Then the line at the back is curling in the upward direction, the line at the front is curling in the downward direction. Hopefully my drawings are working. So the right-hand grasp rule tells us the direction of the magnetic field around a current-carrying conductor. So to find the magnitude of the field, we have a formula which says B, which is the magnetic field strength, equals mu naught, the permeability of free space, which we'll talk about in a minute, I over 2 pi r. Now, technically, at higher levels of physics, that should just be mu. Mu naught is the permeability of free space to magnetic fields, so how easy it is for magnetic fields to go through that particular medium. Other materials have different permeabilities. So if we were doing this in water, inside glass, inside steel, etc., then that value of mu would be different. But air behaves very similarly to free space. So we can use mu naught, the permeability of free space, for any situation where we're working in air. Mu naught is 4 pi by 10 to the minus 7 Tesla meter per ampere. So that's the units. 4 pi, you could actually calculate that out because it's just a number. It's about 12 point something. So you can write mu naught also as 1.26 or 27 by 10 to the minus 6 if you want to. But 4 pi by 10 to the minus 7 is probably easier to remember, actually, and that's the way it's often recorded in books. So B equals mu naught I over 2 pi r. Let's just check out the units. The unit of B, the magnetic field strength, is Tesla, named after Nikolai Tesla. The unit of, well, let's just do it all in units. So the unit of mu naught is Tesla meter per ampere. the unit of I, the current, is just ampere. The unit 2 pi is just the number again, and the unit of r, the radius, the distance away from the line, is meter as well. So meter cancels with meter, ampere to the -1 cancels with ampere, and we have Tesla on the left and Tesla on the right. So the units are consistent, which is encouraging. It's worth doing a quick check on that. Now, if we were to actually do any calculations in this, we end up with 4 pi by 10 to the -7 times I over 2 pi times r. So the 4 and the 2 will cancel out to give us a 2, and the pi's will cancel out. So we end up with 2 by 10 to the -7 I over r, but that's not necessarily anything you need to remember. It's just hopefully a useful thing. So that's the first piece. We know that when we've got a current or a beam of electrons, if this was the beam in an electron gun, we would also have a magnetic field created around moving charge. It's moving charge that creates the field. So we've got that piece. The other piece we can do, and I've done this in the explanation video a little bit, is that if I've got one wire carrying a current in a direction and another wire carrying a current in a direction, then the field due to that top wire is going to be in the same direction as the one we just looked at. So it will go down, around, through where that other wire is. Oh, sorry, that's a very dodgy ellipse. This is our radius r, the distance between the two wires. And at the point where it's passing that wire, remember we said that at the back the field's going upward, at the front the field's coming downward. At the top the field is coming forward out of the page. Oh, well, that's not right. Forward out of the page, kind of hard to draw. At the bottom the field is going backward into the page. So if you imagine the field going basically at right angles to the wire directly into the page at that point. So what have we got there? We've actually got now a current carrying conductor in a magnetic field, so it's going to experience a force, and that force will be given by the right hand palm rule, or just the right hand rule, which we talked about before, which is that if we put our thumb in the direction of the currents moving and our fingers in the direction of the field line, so in this case your thumb is pointing to the right of the screen, your fingers are pointing directly into the screen, and the force is going to be upward. So you're going to, this bottom wire is going to experience a force upward, in other words, toward the other wire. We could actually run that whole argument through from the perspective of the other wire as well, which is look at the field caused by the bottom wire and the effect that it has on the top wire, and we would discover that in fact it pushes down on the top wire. But also Newton's third law about equal and opposite forces acting on different things suggests that if the top wire is exerting an upward force on the bottom wire, then the bottom wire is exerting a downward force on the top wire. So that makes sense, and we could calculate that because we also have F equals BIL, or BIL sine theta is probably a better way to put it, just to make sure that we're in the right angle. But so we know we could work out the magnitude of the field at this point at the bottom using B equals mu naught I over 2 pi r, and then we could put that B into this equation and work out the magnitude of the force on the wire. So hopefully that's a useful little backup video. It's a little extra 10 minutes, but I just wanted to make sure that I had actually covered everything that I'd talked about in the explanation video, and that may or may not be in the Module 3 quiz.